In this video, we are reviewing what is a number according to Richard Dedekind, who is a mathematician famous for Dedekind Cuts, which is a really nice way to think about real numbers. And so we'll go through two of his essays, Continuity and Irrational Numbers, and the nature and meaning of numbers. And I mostly used this version of the book, and what's really interesting is that it's quite old tech, and what you can see is that each of the characters' mathematical symbols were hand drawn, I guess, because they didn't have it in their printer, and so it makes a really nice display where they really stand out, and each of the capital psi that you see here, for example, they are a little bit different. It's really nice to see that somebody actually went through the trouble of going through all of this by hand, which made it really nice. But anyway, the theory of numbers of Dedekind starts with the natural numbers, and it defines the natural numbers in a very interesting way. It starts with a system, which is a collection of things, and then you have an application phi that takes anything and transforms it into another thing. And when you have phi in a system, you can talk about a chain, which is any system where the application phi maps the element of the system inside of the system itself. So it sort of goes inside itself. And that's the base object that he uses. And what's interesting is that if you take any function phi, when it goes inside itself, you could start with the number 1, and then phi of 1 is 2, but then it could start looping, or it could sort of become stationary. And so there's many different things that can happen, but there's one condition that is very simple, and that will make it so that when you start from 1 and you apply phi, you will go through all the natural numbers. And the condition for that is just that phi needs to be injective, so an injection. So whenever you have two elements, they cannot point to the same image, right? Two elements don't point to the same image. And just this single condition with the fact as well that the unit 1 is not in the image of the function phi makes it so that there's at least one number which is not the identity, so 1 goes to another element. And then you can just go through the function phi iteratively, and you will always get another element without repetition, without loops, and so you will go through all the natural numbers. And so that's the way that basically natural numbers are defined. And the example is really interesting because to say that they exist, he says, I'll give you an example of an infinite system. And the example is the system of thoughts and all the objects that can become an object of thought. And it starts with the example that he gives, starts with the ego, so the self, and then you have the metacognition of the ego, which is I think of the self, or then I think that I think of the self, and so forth. And you'll notice that this metacognition is a function phi that takes a thing and that injectively map it to something else, and it applies to all the system of thought. And so through the cogito ergo sum, so the self exists, and then if you think that metacognition exists as well, you have this infinite system with the function phi that actually has the structure of the natural numbers. So cogito ergo sum, so the self exists, and then the metacognition of the self exists, and it can get applied to itself. So that's how Richard Dedekind defines numbers. And what's really interesting is that when you do mathematics with natural numbers, you can prove things with something that's very simple, which is the process of induction. So when you define nicely what is addition of numbers, what is multiplication of numbers, you can always sort of make it so that you can prove things from a base case for n equal 1. And then if you prove that the property is true for any number n, and it will be true for the number n plus 1, since you proved it for n equal 1, it means that it will be true for all the natural numbers. So for all the steps of this function phi, it will remain true, because you show that it's true for a base case, and then that at any point, if you can go to the next level of the iteration of the function phi, let's say. And so all these properties which are arbitrary, which could be seen as arbitrary, like distributivity of multiplication versus addition, all of those stuff, when you define them on the natural numbers, you have a logical system of proof which comes from this induction. And so the natural numbers are very elegant in the way that they ground numbers in one of the basic tool of philosophy, like cogito ergo sum, one of the base principle. And then he just studies this notion of chains that with this injective function, and with the first element 1, which is not included in the first image of the chain, so there will be no loop back to 1, and there will be like always new numbers because the function is injective. And so very elegant and very nice way to prove things about numbers with the induction. So very, very nice. And then when you go through the rational numbers, it just mentions the fact that basically when you can add numbers, then the mind just wants to subtract number. So the number 0 doesn't really exist in his theory of natural numbers, but I think it emerges when you start to want to have the opposite, like the opposite of the addition. And so you start to have this -1, and you have 0, which is like the additive identity. And rational numbers is the inverse of, because you apply the inverse of multiplication. So you have 1 over n or p over q for any numbers. And so, and all of those things that you can define based on the natural number system as a source is really nice, because you can prove things through induction. And then the invention that Dedekind is famous for is a way to, on this very solid edifice, add just one very nice condition to define real numbers, which, they're more real numbers than natural numbers. So you will not have this very simple induction on them. So it's very nice that you can just define something as complex as real numbers, just starting from natural numbers. And the way it does it is through the notion of cuts. And you can, the cuts, basically there is, for all the rational numbers, it's quite easy to think that you can split them into all the rational numbers that are greater or lower than a given rational number. Like if you have a rational number 2, all the rational numbers greater than 2, and all the rational numbers lower than 2. So that's a structure. You can cut all the numbers into 2 portions. And what it says is that to get the real numbers, you just need to say that all of the cuts of the rational numbers, they are actually referring to a number. And so when you have any number, square root of 2, pi, all these irrational numbers, they will also be included in your theorem number because they split exactly the plane in also two system of rational numbers on both sides. And so again, you have a very clear idea, which is just you split rational numbers into two systems, one lower and one higher than the number you're pointing to. And this system is made of rational numbers, which points back to natural numbers where you have very strong language of proof, and real numbers become defined based on the same object, which was clear to begin with. It is based on the same stuff. You just cut the plane into two infinite set of rational numbers. So that's why Richard Dedekind is really well liked. It's a construction of numbers which is really smart. I think it's, for Cartesian mind, it would be one of the best way to define it, right? And you also have this very nice way of thinking. He likes to say that his theory is really not the theory of numbers on a point or on a line. He likes to say it's logic because it's true, like it points it back to logic system. But why his theory is great is that you can picture real numbers on a line as just this point that separates the line in two. So this boundary, you can sort of see it geometrically on the line. So I think that's why also people like it. Not only is it really sort of clear step by step, but you also see it on the line. And so this is all the compliments that we can give. And now let's try to make the critique of the Dedekind Cuts. And the critiques are that basically you define real, to go from rational numbers to real numbers, it's a lot. And the way he managed to talk about real numbers with natural numbers is that he indirectly defines numbers, right? You define the numbers in the middle, pi or whatever, based on all the rational numbers that it is not, right? You have to separate into infinite sets or systems of rational numbers of everything that it is not. And by pointing to that, he says you define the number, but it's still very indirect, right? If you want to define an object, you should define the object, not everything that it is not in the rational number. And it defines, so it doesn't really talk about the object itself, in my opinion. It points to one way to talk about numbers, so it points to a language on how to talk about numbers. But it is not the best way to talk about numbers. The best way to talk about numbers is conventionally the axioms of numbers, which tells you all the properties that you can apply to the number. And the axioms it's a better way to have a language to talk about numbers. What it is not, the axioms is a way to think about the object itself, the object that satisfies the axiom. The axioms gives you some way to formulate propositions about the numbers, but it doesn't tell you this is what x is. It tells you if you have an x, there exists this other x. You can talk about, you can say statements about the number, but you don't really talk about what the object is. And so the Dedekind Cuts, they show you what it is. They show you that it's a boundary on the line, sort of. It's very concrete, but it's indirectly pointing to the object, and it's not the best language to talk about numbers, to prove things about numbers at the end, because axioms are much more direct in that space. And so and it doesn't really tell you what it is. It points to the object in a very indirect way. And by taking a step back, we can see that there's a lot of tricks like every step is clear, but there's a lot of tricks that go on in making it work. And because rational numbers are dense, we call they're dense, like they really surround the real numbers, even though there's 0% of the real numbers. Even natural numbers are 0% of the real numbers. They sort of surround the real numbers, and so they can talk about something that's 0% of the real numbers to point to real numbers, but it makes it so that he never talks about what most of the numbers are, what they are in general, right? It just used the trick that it's very powerful, the rational numbers, because they are dense, and so they can surround a number, and so that's why it surrounds them. It surrounds every real numbers with all the rational numbers, but it's the real numbers carries his own identity, right? And so there's only himself that can talk about himself, and so the rational numbers cannot talk about x, the real number. And so what he uses is that he uses all of the rational numbers, all at the left and all at the right, which is crazy when you think about it. Because the identity now becomes spread all around. It's just because it's sort of a trick by surrounding numbers, and even though it's only this rational number surrounding the number that define the number, it sort of uses all of the other one that he doesn't need, right? To make it work. Because at the end of the day, there's only x, the real number, that can talk about x. And for me, the nail in the coffin, if we were to use that language, is that it tries to give a definition of numbers based on ordering, because you surround the real numbers with these two system of rational numbers. And so you sort of point of the boundary that's greater than all the rational numbers below it and higher than all the rational numbers above it, lower than all above it, and higher than all of the rational number below it. But whenever you think dynamically about real numbers in another way that ordering, this intuition of Dedekind Cuts fail to me quite spectacularly. When you multiply pi by pi with Dedekind Cuts, you have to multiply, because it's such a big thing, you have to multiply all of the rational numbers that exist. All right? So to multiply pi by pi, and because it's so not parsimonious, you have to multiply 9 over 12 by 15 over 12 when you multiply pi by pi, because you have to multiply all numbers below it by the numbers below it, sort of. When you start to use them, these Dedekind Cuts dynamically. And so I think it's a case of step by step it makes sense, and it's brilliant. You start with the ego and the metacognition and everything. So it's sort of everything makes sense step by step, but at the end of the day, you look at the whole, and I think that it doesn't come together. There's too many noise, too many things that makes it weird. That's not how it's supposed to be understood, numbers, you know? And that's when 0, 1 plus infinity comes, because with 0, 1 plus infinity, what we try to do is we try to give an object that carries its identity as a real number. And you have these three constants, 0, 1 plus infinity, that want to emerge, and plus infinity is sort of transcendent, it's not a real number, but and by their definition, you have x, which is the object that makes them take their specific being, the specific spots that they need, 0, 1, and plus infinity, infinity being the only transcendent number, need all the other numbers to actually be that, right? So there's these sort of primary numbers that are quite clear, and you have this specific identity below it that has very clear definition as well, because they just related to these three constants, to the axioms, and it's just a very slight modification of the axiom of the real numbers. And so you have this x, which is, we call space-time, space like the additive axiom, time is sort of the multiplicative axiom. And so you have all these axioms that are understood directly and that are accessible directly to this object x. And you have these three constants that are carries the axiom, which are also defined. And so you have an object-oriented definition of numbers. Right? You talk about x, this thing. You don't talk about everything x is not by using some tricks. Because talking about what is not is like saying, when we talk about the color orange, what we say is that it's just a color orange. And what Dedekind would say is that it's everything that's between red and yellow. And then if you want to know, okay, so what's the color which 3/4 of the wavelength, for example, and Dedekind say, well, no problem, you just multiply all the colors that exist all around, and then you look at the result, and it's sort of the result of that is the color that's between violet and turquoise. And what we say is that no, when you do that operation on orange, you get blue, which is directly what you're talking about. But everything is indirect, and it's not the right way to understand the concept, right? And it's one way to illustrate that. And finally, one of the thing that remains with this definition of numbers is that you have this multiplication which is lacking an inverse for 0, which is not the case because you can define transcendental equation between 0, 1 plus infinity, so that completes sort of the system. And again, the induction is really nice to prove properties about numbers, but it is properties that are defined for 0% of the numbers. So we can also think maybe these properties are more fundamental and expressed on the object of the real numbers themselves. And then you have also this induction that you can have on the natural numbers to prove these properties on simpler case if you need, right? So that's the idea, and so that's why 0, 1 plus infinity is important. It gives you an object-oriented definition of numbers, which is almost directly ties to the best language that we have to talk about the properties of numbers, which is the axioms of the real numbers. And if you need to think about the natural numbers with 0, 1 plus infinity, one way would be to say, well, you can define them much simpler with just an application file, which is injected, for example. And so you don't need to talk about space, time, multiplication, all those stuff. But there's you can think of when you have phi of 1 equals 2. You actually have two slots, and you can say it's the addition going from 1 to 2. It's also the multiplication because you have two slots where 1 appears twice, right? And so you can interpret it as space-time as well as elementary space-time, which is discrete. But whenever you have an addition, you can wrap it into a multiplicative interpretation, which makes it so that you always have specific instances of space-time and teleology whenever you look at this simple stuff that you can study and make a theory of natural numbers with. And basically, when you put all of this together, what you have to see is that all these steps that seemed clear in natural numbers, they bring objects that are not good enough to think clearly about real numbers, about cases that are more complex. And so you start to think, I need to start with an object definition or action that are at a higher level, and start to interpret the lower level properties as sort of basic version of it, but which reproduce something that remains fundamental at a higher level, basically. And so that's our critique of the Dedekind Cuts. Again, very nicely done, very convincing. It's just when you put it all together, you start to see some flow, and you start to notice maybe a lot of tricks have been used to make it work. And you need some theory that is much more parsimonious, much more direct to the point, gives you objects, you talk directly about the object X, and with the language that will be the dynamically the most direct, meaning the number multiplies directly, pi multiplies directly. It doesn't need to multiply all the rational numbers around it that exist between a lot of them to get to the right solution. Right? That was the review of Dedekind. I think we'll review as well the set theoretic definition of numbers and a couple of others which are classic to really give you a good idea of where we stand on all these definitions and how to think, how to respond as well to what's the point of defining number with three constant. We think there's a lot of progress there, and we want to make sure that we understand well what we could have missed from these other theories, and also bring up our particular perspective to all of the theories as well. Thank you for watching, and have a good one.